The captured American tank rolled to a stop in the sandy testing grounds south of Berlin, and something fundamental shifted in the confidence of the Third Reich's engineering corps. They had painted German crosses over the white American stars, slapped on Wehrmacht license plates, and designated it Beutefahrzeug 259, Captured Vehicle 259. But no amount of German markings could hide what this machine represented, and what it was about to reveal would haunt every engineer, every general, every armaments minister who saw the testing reports that would follow. This wasn't just another enemy tank brought back for evaluation. This was physical evidence of a crisis that had been building for 2 years, one that Germany's leadership had desperately tried to ignore, explain away, or dismiss as Allied propaganda. The mathematics of armored warfare were about to be rewritten, and the equation wouldn't involve firepower, armor thickness, or tactical doctrine. It would come down to something far more mundane, far more embarrassing, and far more devastating to German confidence than anyone watching that Sherman roll off the transport rail car could possibly imagine. The tank bore a name painted on its hull, War Daddy 2, serial number USA 306-7641, built by Lima Locomotive Works in Ohio, belonging to Company G of the 1st Armored Regiment, 1st Armored Division. It had been captured intact during the Battle of Sidi Bouzid in Tunisia in mid-February 1943, when Rommel's forces had briefly turned the tables on inexperienced American units still learning the brutal realities of desert warfare. German reconnaissance personnel had climbed into the abandoned Sherman, fired up its Continental R975 radial engine, and started driving. What happened next should have been routine. A short drive to the nearest German field headquarters for preliminary evaluation before shipping to Germany. Instead, those German soldiers drove War Daddy 2 350 kilometers across North African terrain to the port of Sfax, a journey that took 4.5 days through desert sand, rocky wadis, and the kind of punishing conditions that routinely destroyed German vehicles. And here's what should have terrified every German officer who heard about that journey. The Sherman never overheated, never broke down, never required more than basic refueling stops. The engine maintained consistent power, the transmission shifted smoothly through all 5 forward gears, the final drives, those critical components connecting engine power to track movement, performed flawlessly under sustained stress that would have annihilated comparable German systems. German tank crews who watched this enemy vehicle simply work without complaint through 4.5 days of continuous operation were experiencing something they couldn't quite articulate, but it gnawed at them. They were accustomed to frequent mechanical stops, even on short movements. Their own Panzer IVs required careful nursing to complete long road marches. The new Panther tanks, rushed into production to counter Soviet T-34s, were breaking down so frequently that some units reported barely 20% operational readiness. And here was this American tank, designed by automotive engineers in Detroit and built by locomotive manufacturers in Ohio, performing multi-day journeys across hostile terrain without a single mechanical failure. The implications were staggering, but most German officers weren't ready to confront them. Not yet. That would come later, after the testing, after the measurements, after the meticulous German engineering establishment had dissected every component and been forced to acknowledge what they'd found. For now, War Daddy 2 was loaded onto a cargo ship bound for Germany, with explicit orders from the Army Weapons Office that this tank must reach the testing facility at Kummersdorf intact and operational. German intelligence had received fragmentary reports about American tank production numbers, figures so astronomical they seemed like obvious propaganda. But seeing the physical vehicle made those statistics feel real in ways that numbers on paper never could. The Sherman represented something Germany fundamentally wasn't, a nation with such profound automotive industry maturity that they could translate mass production principles directly into tank manufacturing without losing quality or reliability. As that cargo ship steamed northward across the Mediterranean in spring 1943, Wehrmacht engineers were preparing testing protocols that would expose truths they'd been reluctant to face about their own limitations and American capabilities. They were about to discover that the United States hadn't just built more tanks than Germany, they'd built better tanks in the way that actually mattered for sustained military operations. and the evidence was about to roll off a rail car in Brandenburg, bearing German markings but American engineering, ready to demonstrate exactly how far behind Germany had fallen in the industrial war that would ultimately decide everything. When War Daddy 2 arrived at the Kummersdorf proving ground 25 kilometers south of Berlin, it entered a facility that represented the pinnacle of German military engineering assessment. Kummersdorf was where German superiority was supposed to be proven, where meticulous scientists and engineers measured, tested, and validated the technological advantages that Nazi propaganda constantly proclaimed. The facility had hosted every significant German tank design, every captured Soviet vehicle, every piece of equipment that Wehrmacht forces encountered on battlefields from North Africa to the Eastern Front. Teams of specialists descended on captured equipment with precision instruments, exhaustive documentation protocols, and the kind of methodical thoroughness that German engineering culture prided itself on. They photographed every component from dozens of angles, measured every clearance with calipers and micrometers, documented construction techniques and material specifications. This was where German technical superiority was supposed to be demonstrated through objective scientific analysis, where enemy equipment would be found wanting when measured against exacting Teutonic standards. Instead, Kummersdorf was about to become the site of a reckoning that would shake German confidence to its foundations. The initial inspection team started with the transmission because that's where German tanks consistently failed, and where German engineers expected to find evidence of American industrial shortcuts and inadequate design. What they found instead contradicted everything German doctrine had accepted about the necessary trade-offs between performance and manufacturing complexity. The Sherman used herringbone-cut gears throughout its transmission and final drives, gears where the teeth were cut in a V pattern that distributed stress across multiple contact points simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with relatively loose manufacturing tolerances. The gears were nearly impossible to strip because the load was spread across so many teeth at once, and they ran quietly compared to the straight-cut gears German transmissions employed. German engineers had known about herringbone gears for decades. The principle wasn't some American secret or revolutionary innovation. They'd considered using them in German tank designs and rejected the approach because herringbone gears were deemed too difficult to mass produce, given Germany's industrial capabilities and workforce training. The cutting process required specialized machine tools and careful setup. The manufacturing tolerances, while less demanding than straight-cut gears, still required quality control that German factories struggled to maintain under wartime production pressures. The Americans had been manufacturing herringbone gears by the thousands for civilian automobiles, farm tractors, and industrial equipment throughout the 1930s. When war came and tank production ramped up, American industry simply applied existing manufacturing expertise to military requirements without the transition causing any particular difficulty. General Motors, Ford, Chrysler, Caterpillar, these companies had decades of experience mass-producing complex automotive components to consistent quality standards because American civilian life demanded it. Millions of Americans owned cars and expected them to work reliably with minimal maintenance. That consumer expectation had created an entire industrial ecosystem optimized for producing mechanical components that functioned correctly under real-world conditions, not just on engineering drawings. Germany had no such ecosystem because Germany had never developed mass automobile ownership. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. Most Germans had never owned a car, never maintained a car, never developed the intuitive mechanical understanding that came from living in an automotive culture. German tank designers were brilliant theoreticians working in an industrial environment that lacked the practical manufacturing maturity to execute their designs reliably at scale. The testing began in earnest as spring turned to summer in 1943, and every trial produced results that German engineers documented with growing unease. They drove War Daddy 2 through obstacle courses designed to replicate battlefield conditions: steep slopes, loose sand, rocky terrain, sharp turns under load. They measured fuel consumption, monitored engine temperatures through hours of continuous operation, recorded transmission behavior under varying loads. After each trial, they disassembled components to examine wear patterns, looking for stress fractures, inadequate lubrication, or design weaknesses that would manifest over time. What they found was a transmission that performed adequately in every category and excelled in the one metric German tanks consistently failed: operational endurance without maintenance intervention. The Sherman transmission featured 5 forward speeds plus 1 reverse, with synchronization in gears 2 through 5. That synchronization, borrowed directly from civilian automobile design, eliminated the need for double clutching during normal operations. Shifting gears in the Sherman was nearly as easy as shifting gears in a Buick sedan or Ford truck. This made the tank simple to drive for soldiers with basic automotive knowledge, requiring minimal specialized training. German tankers, by contrast, spent considerable time learning complex double-clutching techniques and careful throttle management just to avoid damaging their transmissions. The unsynchronized, straight-cut gears in German tanks required precise matching of input and output shaft speeds during shifts, a skill that took practice to master and concentration to maintain under combat stress. Miss the timing, and you could strip gears or cause damage that would require field maintenance or even complete transmission replacement. The Sherman's design accepted that ordinary American conscripts, farm boys who'd driven tractors, factory workers who'd operated delivery trucks, teenagers who'd learned to drive the family car, would operate these machines with whatever skill level they brought from civilian life. German designs assumed highly trained specialists would be available, specialists who'd spent months in technical schools learning the intricacies of German tank operation. This fundamental philosophical difference in design approach reflected broader assumptions about industrial capacity, training pipelines, and the kind of war each nation expected to fight. America designed for mass mobilization of citizen soldiers who'd receive adequate training but not extensive technical specialization. Germany designed for smaller numbers of elite troops who'd receive intensive training on complex equipment. One approach scaled to total war mobilization, the other didn't. The Continental R975 radial engine in War Daddy 2 demonstrated the same pattern: adequate performance maintained across operating conditions that caused German engines to fail. German test engineers noted that the Sherman's engine maintained consistent power output across temperature ranges that would have caused Maybach engines to overheat or lose power. Cooling system, though relatively simple in design, proved highly effective through passive airflow and well-designed ducting. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa, where fine sand infiltrated everything and required constant maintenance to prevent engine wear. Every system reflected a design philosophy that prioritized practical functionality over theoretical optimization, real-world reliability over impressive specifications. The Americans had built a tank that worked correctly under field conditions because American automotive engineers understood through decades of practical experience what working correctly actually meant in practice. It meant functioning when needed without requiring expert intervention, continuing to operate under abuse and neglect, maintaining performance even when maintenance schedules slipped due to combat tempo or supply shortages. June 1943 brought what should have been a triumph of German engineering, a demonstration at Hillersleben artillery range where Reichsminister Albert Speer would observe German tanks performing alongside captured Allied vehicles. Speer, personally responsible to Hitler for armaments production and desperate to demonstrate that German industry could match Allied output, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration program included hill climbing trials comparing German and Allied tanks, with War Daddy 2 sitting alongside Germany's latest and most advanced armored fighting vehicles. The Panther Offs D medium tank, fresh from production and representing Germany's answer to the Soviet T-34, would demonstrate its capabilities. The Ferdinand tank destroyer, a 70-ton monster mounting an 88mm gun in a fixed casement, would show the ultimate expression of German heavy armor philosophy. These were the vehicles that German propaganda proclaimed as technologically superior to anything the Allies fielded, proof that German engineering excellence would overcome material disadvantages. The Sherman would presumably demonstrate its inferiority through failure to match German performance, providing reassurance that American mass production was producing quantity over quality, numbers without substance. The Sherman climbed the test slope smoothly, its synchronized manual transmission shifting without hesitation as the driver worked through the gears. The Continental engine maintained consistent power delivery throughout the ascent, never lugging or struggling. The driver handled the vehicle with casual confidence, demonstrating the ease of operation that made the Sherman so effective with crews that had received only basic training. It wasn't a particularly dramatic performance. The Sherman simply drove up a steep slope the way tanks were supposed to, without fuss or difficulty. The Panther followed its more powerful 700-horsepower Maybach HL230 engine, allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The driver worked carefully through the unsynchronized gears, double-clutching to avoid transmission damage. The engine labored audibly under the 45-ton vehicle's weight, and observers noted that the Panther seemed to be working much harder than the lighter Sherman to achieve comparable results. Then came the Ferdinand's turn, and what happened next would become legendary among German armored officers as an example of everything wrong with German tank development. The massive 70-ton vehicle started up the incline. Its electric transmission system, theoretically superior to mechanical transmissions, handled the initial slope without difficulty. Halfway up, the Ferdinand stalled. The engine overheated. The electric motors couldn't sustain the power draw. Recovery crews rushed forward to restart the vehicle while Speer watched with dozens of senior Wehrmacht officers and industrial leaders. The embarrassing failure was occurring before an audience that included everyone who mattered in German armaments production. Speer would write about Sherman capabilities years later in his memoirs, carefully noting that reports on the cross-country mobility of the Sherman had been very favorable. He observed that the Sherman could climb mountains that German tank experts considered inaccessible to tanks, attributing this to the Sherman having a very powerful motor in proportion to its weight. The public assessment that appeared in Das Reich newspaper on June 27, 1943, described the Sherman as, quote, one of the special accomplishments of the North American laboratories, and called it quite a praiseworthy product of the North American steel industry. These carefully worded statements, crafted for propaganda purposes to avoid appearing defeatist, nevertheless concealed private alarms spreading through German engineering departments. The Sherman wasn't just adequate, it was fundamentally better engineered for sustained field operations than German tanks that cost more to produce, required more scarce materials, and demanded far more maintenance. The question that nobody wanted to ask publicly, but everyone was thinking privately, was this: if American industry could produce tens of thousands of tanks that performed this reliably, while also producing everything else needed for a global war, how could Germany possibly win an industrial contest against such an adversary? Back at Kummersdorf through summer and autumn 1943, systematic testing continued with German thoroughness, and every measurement added evidence to a conclusion that German engineers found increasingly difficult to avoid. They conducted extended trials measuring operational range, pushing the Sherman through thousands of kilometers of operation. The results documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank, with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing so simple that inexperienced drivers could operate the tank effectively after minimal training. They tested the final drives under sustained stress, subjecting them to loads and operating conditions that would destroy German final drive systems within 200 kilometers of operation. The Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed even under sustained combat conditions that would have been catastrophic for German components. Restoration projects decades later would find Sherman final drives that needed no mechanical restoration after years of storage, testament to design margins that exceeded immediate requirements by substantial factors, insurance against field conditions, and maintenance lapses. The final drives presented perhaps the most devastating comparison for German engineers who understood the implications. German Panther tanks employed final drive systems inherited from Tiger design, a configuration that had been pushed beyond its safe operating limits to handle the Panther's 45-ton weight. The design used straight-cut gears and housings that proved inadequate for the sustained loads that combat operations imposed. German mechanics in North Africa and on the Eastern Front had reported final drive breakdowns, forcing Panthers to be abandoned after relatively short movements, sometimes less than 100 kilometers from their starting point. Field commanders learned through bitter experience that Panthers couldn't be counted on for long approach marches. The final drives would fail from fatigue and stress before the tanks reached combat. This meant Panthers had to be transported by rail whenever possible, saving the precious remaining component life for actual battle rather than consuming it during movement to the battlefield. The Sherman's final drives, by contrast, were so overbuilt relative to the vehicle's weight and power that they essentially never failed from mechanical stress. American tankers could drive their Shermans hundreds of kilometers across rough terrain, engage in combat operations, and immediately continue movement without waiting for maintenance. The operational flexibility this provided was incalculable. American commanders could position forces, reposition them based on changing tactical situations, pursue retreating enemies, and maintain operational tempo that German forces simply couldn't match given their mechanical limitations. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches and armaments ministry offices. These documents, stamped with security classifications and intended only for senior officers and officials with appropriate clearances, painted a sobering picture of comparative capabilities that contradicted nearly everything German propaganda told the public about Allied industrial inadequacy. The reports documented that the Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite possessing equivalent theoretical knowledge and scientific expertise. German engineers understood mechanical principles as well as their American counterparts, arguably better in many theoretical aspects. They simply couldn't translate that knowledge into reliable hardware at mass production scales because German industry had never developed the manufacturing ecosystems that decades of civilian automotive production had created in America. The reports noted that American mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. What made these findings particularly devastating was understanding how they reflected broader industrial realities that Germany couldn't change through effort or will. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership with vehicles commonplace among ordinary citizens across all economic classes. By 1940, America had roughly 30 million registered automobiles for a population of 130 million, nearly one car for every 4 people, including children. Working-class families owned cars, farm families owned cars or trucks. Teenagers learned to drive and maintain vehicles as routine parts of American life. This created enormous demand for automotive components, repair services, and aftermarket parts, an entire industrial ecosystem serving civilian transportation needs. That ecosystem had matured over 3 decades, developing manufacturing techniques, quality standards, and practical engineering knowledge that couldn't be replicated quickly because it represented accumulated generational experience. Germany, by contrast, had far more limited civilian automotive experience, with cars remaining luxury items for the wealthy and party elite through the 1930s. The Volkswagen program that had been promised to German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939, when war production took priority over consumer goods. Most German soldiers had never owned a car, never changed oil, never replaced spark plugs, never developed the intuitive mechanical understanding that American soldiers brought from civilian life. The system included a backup generator that could power turret traverse even when the main engine stopped, a feature that seemed like unnecessary luxury to German designers, but proved invaluable in combat situations where engines stalled on slopes or were damaged by enemy fire. German tankers could only dream of such conveniences, particularly those who would experience turret traverse failing when engines stalled, leaving them unable to track targets or return fire effectively. These features didn't appear in German technical specifications because German designers had never considered them high priorities compared to armor thickness and gunpowder, the metrics that looked impressive on paper and could be touted in propaganda. But combat revealed which features actually mattered for tactical effectiveness, and backup systems that kept weapons functioning under degraded conditions proved more valuable than thicker armor that added weight without adding reliability. The comparison with German tank reliability became impossible to ignore as field reports accumulated through late 1943 and into 1944, painting a picture of German armored forces crippled not by enemy action, but by their own equipment's refusal to function correctly. Panther tanks required strict operational restrictions to prevent mechanical failures that would leave them stranded far from repair facilities. Drivers received explicit instructions documented in field manuals. Do not change gears frequently, as excessive shifting damaged the transmission. Avoid using third gear except when absolutely necessary, because third gear failures were so common that using it represented an unacceptable risk. Never turn while backing up, as this would destroy the transmission immediately. Limit pivot turns to situations where ground resistance was equal on both tracks. These weren't suggestions. These were mandatory restrictions issued by field commands desperate to keep their limited operational vehicles functioning. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance to clear, meaning Panthers had to avoid terrain that Shermans could traverse without concern. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide, representing the finest that German industry could produce under wartime conditions. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, who approached tank development as an automotive engineering problem rather than a specialized military project. They applied mass production principles developed over decades of civilian vehicle manufacturing, leveraging existing supply chains and manufacturing expertise rather than creating new specialized systems from scratch. The transmission came from multiple manufacturers, including Caterpillar Tractor, Buick Motor Division, and Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. A Caterpillar transmission could be swapped into a tank originally fitted with a Ford transmission, and everything would bolt together perfectly with no modification or fitting required. This standardization, absolutely routine in American automotive industry, where parts interchangeability had been standard practice since Henry Ford's assembly lines in the 1910s, remained largely theoretical in German tank production. Each German manufacturer introduced subtle variations that prevented true parts interchangeability. A Maybach engine from one production batch might require different mounting brackets than engines from another batch. ZF transmissions from different factories needed different connections. Final drives from various suppliers had incompatible specifications. German field maintenance units kept extensive cross-reference charts trying to track which parts worked with which vehicles, adding complexity to logistics systems already strained beyond capacity. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944 as German forces retreated across multiple fronts, each captured vehicle providing more data points confirming American automotive superiority. Shermans taken from British units in Italy underwent testing. Diesel-powered M4A2 variants captured from Soviet forces on the Eastern Front revealed American diesel engine technology that exceeded anything German industry had produced for tank applications. The British Firefly variant, mounting a 17-pounder anti-tank gun, demonstrated growth potential built into the original Sherman design that German engineers had never considered when specifying their vehicles. The Firefly's significantly larger gun fit into the Sherman's turret with minimal modification because American designers had built-in margin, extra space, stronger mounting points, reinforced structure beyond immediate requirements. This reflected American engineering philosophy of overbuilding to provide upgrade potential and reliability margin. German engineers tended to calculate such overbuilding as waste, excess capacity that increased production cost and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. A Sherman designed to mount a 75mm gun could accommodate a 17-pounder because the original design had been robust enough to handle significantly more stress than minimum requirements demanded. The Panther, rushed into production to counter Soviet tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. The design had been optimized so thoroughly for its initial specifications that growth potential had been engineered out. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions and sustained operations that armored units would experience in actual warfare. Engineers drove Shermans through hundreds of kilometers of cross-country movement without maintenance stops, recording every mechanical incident, component failure, and performance degradation. They compared results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts, matching laboratory testing against real-world combat data to validate findings. The numbers told an unambiguous story that no amount of propaganda could obscure. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25% during the worst periods. Individual Panther battalions documented timeframes when fewer than 1 in 5 tanks were actually capable of combat operations, with the remainder broken down awaiting parts, undergoing repairs, or so mechanically unreliable that commanders refused to commit them to operations. The numbers from Operation Citadel at Kursk in July 1943 were particularly devastating. Panthers achieved only 16% operational readiness, with mechanical failures eliminating more tanks than Soviet action. By December 1943, readiness had improved to 37%. February 1944 reports showed 37% operational. April 1944 reached 50% operational. May 1944 finally achieved 78% operational readiness, presented in Wehrmacht reports as a success story, demonstrating that German engineering had overcome initial teething problems. But even that improved 78% operational rate, achieved only after 18 months of field modifications, manufacturing improvements, and accumulated experience, merely brought Panthers to readiness levels that Shermans had exceeded from initial production in 1942. German engineers were celebrating achievements that represented American baseline performance, standards that American tanks met without particular difficulty because they'd been designed from the beginning for reliability, rather than having reliability added as an afterthought following catastrophic field failures. Engine lifespan comparisons revealed the same pattern of German equipment failing to meet standards that American equipment exceeded effortlessly. Sherman diesel variants achieved engine life exceeding 3,000 kilometers under proper maintenance, and often significantly more with the robust Continental and General Motors engines tolerating neglect and abuse that would destroy more temperamental power plants. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems that had seen Maybach HL230 engines failing after just a few hundred kilometers of operation. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented as a significant success in internal Wehrmacht communications. This improvement merely brought Panther engines to roughly one-third of Sherman diesel capability, and diesel Shermans weren't even the variants American forces preferred. The U.S. Army considered diesel engines less reliable than gasoline power plants and relegated diesel production to Lend-Lease for Soviet and British forces. The tanks that America sent to allies as second-choice options were more reliable than the best engines German industry could manufacture. Sherman transmissions required minimal maintenance between overhauls, with synchronized gears that made driver error less likely to cause damage even when crews were exhausted, stressed by combat, or inadequately trained. Panther transmissions demanded constant attention and frequent repair, with third gear failures so common that experienced drivers learned to skip from second gear directly to fourth gear to avoid using the problematic ratio entirely. This wasn't officially documented in manuals. It was folk knowledge passed between veteran crews, tribal wisdom about how to nurse temperamental machines through operations without catastrophic failure. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation, and this single failure point crippled German armored operations more than any tactical defeat. A Panther with a failed final drive wasn't damaged, it was dead, immobilized and useless until a recovery vehicle could tow it to rear area workshops with specialized equipment and trained mechanics capable of replacement.
Those workshops were increasingly overwhelmed by the volume of breakdowns, creating backlogs that meant vehicles sat disabled for weeks awaiting repairs. Meanwhile, Sherman crews were fighting, moving, and maintaining operational pressure that German forces couldn't sustain because too many of their tanks were broken. Field reports from German units that captured and operated Shermans provided the final confirmation of American automotive superiority from the German perspective, and these reports carried particular weight because they came from combat veterans with direct comparative experience. German mechanized units, desperate for reliable vehicles as their own tank inventory degraded through attrition and irreplaceable losses, eagerly employed any captured American tanks they could obtain intact and operational. Unlike Soviet T-34 tanks, which Germans modified extensively before placing them in service, adding commanders' cupolas, replacing radios, modifying controls, Shermans entered German service without changes because they worked correctly as designed. They didn't require modification to be usable, they required only German markings to avoid friendly fire. This contrast spoke volumes about relative design maturity. Soviet tanks needed extensive modification because they'd been designed for Soviet tactical doctrine, Soviet crew training, and Soviet maintenance infrastructure. American tanks needed no modification because they'd been designed to universal standards of automotive functionality that transcended national differences. A German mechanic could maintain a Sherman using the same principles he'd learned on civilian vehicles because the Sherman was fundamentally just an armored vehicle built using conventional automotive engineering. A German tanker could operate a Sherman effectively because the controls, instrumentation, and handling were intuitive to anyone with basic mechanical knowledge. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. This psychological burden affected combat performance in ways that couldn't be quantified in technical specifications, but deeply impacted tactical effectiveness. Confidence that your vehicle would function when needed allowed aggressive tactics and bold maneuvers. Constant concern about mechanical reliability created cautious, conservative tactics, where commanders husbanded their limited operational vehicles rather than committing them fully to decisive action. The mathematics were brutally simple. An aggressive attack that risked vehicle damage through maneuver made sense if you expected the vehicle to be operational tomorrow. That same attack became reckless if vehicle breakdown was likely, regardless of enemy action. German commanders found themselves fighting not just Allied forces, but also their own equipment's refusal to function reliably, a two-front war where the mechanical front consumed resources and attention that should have been directed at tactical problems. The 10th SS Panzer Division captured 12 M4A3 Shermans at Herlesheim in January 1945 during Operation Nordwind, Germany's last major offensive in the West. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault, vehicles left behind in the chaos of retreat that German forces immediately put into service. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war, operating alongside German tanks in the final desperate months as Allied forces closed in from all directions. These captured tanks served as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance stops and reliable mechanical performance over extended operations. German commanders recognized what Kummersdorf testing had proven years earlier. American tanks could be relied upon to function when needed, and that dependability made them more valuable for certain missions than German tanks with superior firepower. A Sherman arriving at the objective with an operational gun was infinitely more useful than a Panther with a better gun broken down 20 kilometers behind the lines, unable to influence the battle. In the final accounting of tactical utility, the weapon that arrives wins, while the weapon that breaks down loses, and German forces facing overwhelming Allied superiority learned this lesson through bitter experience, as their most powerful tanks sat disabled, while inferior American vehicles maintained relentless operational pressure. January 1944 brought expanded testing programs as Wehrmacht forces retreated across multiple fronts and additional captured equipment reached Kummersdorf from Italy, France, and the Eastern Front. Engineers examined the M4A1 with the Continental R975 radial engine, documenting characteristics that War Daddy II had first demonstrated.
They tested the M4A2 with twin General Motors 6046 diesel engines, noting superior fuel efficiency and different operating characteristics that made this variant particularly valuable for extended operations where fuel supply was limited. They evaluated the M4A3 with the Ford GAA V8 gasoline engine, which American crews considered the best Sherman power plant for its combination of reliability, power output, and ease of maintenance. Every variant demonstrated the same fundamental characteristic that had emerged from 2 years of testing: excellent automotive reliability derived from sound engineering principles and quality manufacturing processes that German industry couldn't replicate under wartime conditions. The consistency across variants impressed German engineers, who were accustomed to significant quality variations between different manufacturers producing nominally identical vehicles. A Panther from one factory might have different reliability characteristics than a Panther from another factory because manufacturing standards varied, quality control differed, and component
sourcing created subtle variations in specifications. Sherman production, by contrast, maintained consistent quality across dozens of factories, producing thousands of vehicles monthly because American manufacturing infrastructure enforced standardization through established industrial practices. The diesel-powered M4A2 particularly impressed German engineers who examined multiple examples captured from Soviet forces. The twin GM 6046 diesel engine provided performance matching any Sherman variant, while consuming substantially less fuel than gasoline engines, a critical advantage as German fuel supplies dwindled and synthetic fuel production struggled to meet demand. German designers had experimented with diesel tank engines before the war, but abandoned the effort due to manufacturing difficulties and the complexity of fuel injection systems that required precision machining and specialized components. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules or creating bottlenecks, demonstrating manufacturing flexibility and technological sophistication that German industry never achieved during wartime conditions. The fact that America was building diesel tanks as a secondary option for export, while Germany couldn't build diesel tanks at all, revealed the industrial capability gap that would ultimately prove decisive. Germany was struggling to manufacture adequate quantities of conventional gasoline engines, while America was casually producing both gasoline and diesel power plants in whatever quantities Allied nations requested, switching between configurations as easily as changing production line tooling. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops and one of the fathers of German armored warfare doctrine, noting in official communications that improvements to Panther reliability had achieved what he termed acceptable standards. Engine life had reached 700 to 1,000 kilometers. Final drive problems had been largely resolved through design modifications and improved manufacturing processes, and operational readiness was climbing toward 50% across Panther-equipped units. Guderian presented these achievements as evidence that German engineering had overcome initial difficulties and that the Panther was now ready for sustained combat operations at scale. But this assessment, while technically accurate, revealed how far German standards had fallen and how completely German leadership had lost perspective on what constituted adequate performance. Celebrating the achievement of 700 to 1,000 kilometer engine life meant celebrating a standard that Sherman had exceeded from initial production in 1942, nearly 2 years earlier. Presenting 50% operational readiness as success meant accepting that half of Germany's most modern tanks would be unavailable for combat on any given day, a rate that would have been considered catastrophic failure in American armored units. The German army was celebrating reaching standards that American tanks had exceeded from the beginning, highlighting how comprehensively German tank development had fallen behind and how desperately German leadership needed to believe their equipment was competitive despite overwhelming evidence to the contrary. The comparison grew more painful as German tank production struggled with increasing resource shortages and Allied strategic bombing targeted key bottlenecks in the Panther and Tiger production chain with devastating effectiveness. The Maybach engine plant in Friedrichshafen suffered severe damage from Royal Air Force Command on the night of April 27-28, 1944, a raid involving 322 aircraft that Imperial War Museum archives describe as the most damaging raid on German tank production of the entire war. The attack destroyed not only the engine plant but also the adjacent ZF gearbox factory, eliminating both critical components simultaneously in a single night of precision bombing. Production of tank engines and transmissions halted completely for 6 months, and when production finally resumed in November 1944, quality control had degraded significantly from pre-war standards. Slave labor, increasingly employed in German tank factories as German workers were conscripted for military service to replace catastrophic losses on the Eastern Front, introduced deliberate sabotage that German overseers struggled to detect and prevent. Cigarette filters were jammed into oil passages where they would block lubrication flow and cause bearing failures hours or days later. Gaskets were installed incorrectly, creating leaks that wouldn't manifest immediately during factory testing. Components were assembled without proper clearances, creating friction points that would accelerate wear and cause premature failure. These problems never affected Sherman production. Safely located in American factories thousands of kilometers from any combat zone and staffed by motivated workers earning good wages under decent conditions, workers who took pride in their contribution to the war effort and had every incentive to produce quality equipment that would protect American soldiers. The fundamental difference between American and German tank production lay not in engineering knowledge or theoretical understanding. German engineers were among the world's finest, possessing extensive scientific expertise and deep theoretical knowledge of mechanical principles. They understood automotive engineering as well as their American counterparts, arguably better in many respects, given Germany's strong tradition of technical education and scientific research. They simply never applied those principles consistently to tank design in ways that prioritized reliability over performance specifications, and German industry lacked the manufacturing maturity to execute reliable mass production even when designs were sound. German tanks emphasized performance characteristics that made for impressive specifications but poor reliability in field conditions that exposed every design weakness through sustained operation under stress. The Panther's powerful 75mm KWK-42 gun and thick frontal armor that could defeat most Allied tank rounds came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's 45-ton weight through extended operations. The transmission, final drives, and engine were all pushed beyond their safe operating limits by a vehicle that had grown heavier during development as armor protection was increased without proportionally strengthening the drivetrain components. The Tiger's formidable capabilities that made it feared across every battlefield where it appeared demanded complex maintenance procedures and frequent repairs by highly trained specialists with years of technical education, specialists who were increasingly scarce as casualties mounted and experienced personnel were killed, wounded, or transferred to infantry units desperate for manpower. These trade-offs might have been acceptable if German industry could produce enough vehicles and enough spare parts to maintain them in field service at scales that matched operational requirements. It could not, particularly as Allied bombing intensified and raw material shortages worsened through 1944 and into 1945. Chrome for armor hardening became scarce, forcing use of inferior alloys that couldn't match specified protection levels. High-quality bearing steel was diverted to aircraft and submarine production, leaving tank manufacturers with substitutes that wore faster and failed sooner. Copper for electrical systems was increasingly replaced with aluminum that had higher resistance and inferior conductivity. Every material substitution degraded performance and reliability further, creating a death spiral where German tanks became progressively less capable, even as propaganda proclaimed each new variant as superior to its predecessor. American engineers trained in automotive mass production through decades of civilian industry experience designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life before military service. The Sherman powertrain used components proven in commercial service with design principles borrowed directly from automobile and truck manufacturing that had been refined over decades of competition in civilian markets. The electrical system included redundancies and backup systems that seemed like unnecessary luxuries to many European engineers.
To German designers focused on minimizing weight and complexity, but proved invaluable in combat conditions where damage, wear, or operator error could disable primary systems. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became increasingly scarce, with supply systems breaking down under strain of Allied bombing and transportation disruptions. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches that would consume the limited remaining service life before combat.
Field commands issued explicit orders restricting Panther movement to preserve the vehicles for actual combat, rather than losing them to mechanical failure during approach marches to the battlefield. The Berger Panther recovery vehicle, built on a Panther chassis specifically to recover disabled Panthers from the battlefield, shared the same final drive reliability problems as the tank it was supposed to recover, meaning recovery operations risked losing the recovery vehicle alongside the disabled tank being recovered. German commanders faced the grim reality where mechanical failures eliminated more tanks than enemy action, with some units reporting that 70% of tank losses were due to breakdowns rather than combat damage. This statistic was buried in classified reports because admitting such catastrophic mechanical unreliability would undermine troop morale and contradict propaganda about German technological superiority. But the numbers couldn't be hidden from commanders who watched their available combat power evaporate through mechanical attrition regardless of tactical success or failure in actual engagements with enemy forces. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match, even before strategic bombing had degraded manufacturing capacity. American factories produced 49,324 Sherman tanks during the war years, more than all German tank production of all types combined from 1939 through 1945. British Commonwealth forces received thousands of Shermans through Lend-Lease, equipping entire armored divisions with American vehicles that proved more reliable than British tank designs. The Soviet Union received over 4,000 diesel M4A2 variants that served alongside T-34s and proved particularly valuable in exploitation operations, where sustained movement without maintenance stops allowed rapid advances. Chinese forces in Burma used Shermans to devastating effect against Japanese armor that was technologically inferior to both American and German designs. Vehicles that had been adequate for operations against China in the 1930s, but were hopelessly outclassed by 1944 standards. Every theater where Sherman served confirmed what Kummersdorf testing had revealed in 1943. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. And even improperly maintained Shermans often continued functioning through neglect and abuse that would have been fatal to more temperamental vehicles. The Sherman's tolerance for maintenance lapses, battlefield damage, and operator error meant that it remained effective even under degraded conditions that rendered German tanks useless hulks awaiting recovery that might never come. German tank crews who captured and used Shermans universally praised their automotive excellence in letters home, official reports, and post-war interviews that documented their experiences with both German and American equipment. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler A57 multibank engine, with its 5 separate engine blocks arranged in a star pattern, 30 cylinders total, and intricate plumbing connecting everything, easier to troubleshoot and maintain compared to German tank engines that required specialized knowledge and equipment to service correctly. The A57, which American mechanics generally disliked for its complexity, and which was discontinued after early production runs, represented one of the worst Sherman power plant options from the American perspective. German mechanics who examined captured tanks with A57 engines thought they were remarkably straightforward and user-friendly compared to the Maybach engines they worked on daily, engines that required constant adjustment of valve clearances, precise ignition timing, and carburetor settings that drifted out of specification under field conditions. The Ford GAA V8, praised by Allied crews for its exceptional reliability and power output that provided excellent performance across all operating conditions, seemed almost miraculous to German mechanics, accustomed to temperamental power plants that needed expert attention. The General Motors twin diesel, which the U.S. Army had rejected as less reliable than gasoline engines and relegated exclusively to Lend-Lease production for Allied nations, far exceeded the performance and reliability of any diesel engine German industry had produced, or even attempted to produce for tank applications during the war years. The Sherman's generous design margins provided another advantage that German engineers came to appreciate once they understood the philosophy behind American overbuilding. The basic transmission and final drive components originally specified for the 30-ton M4 with 400 horsepower required no major modification to handle the 42-ton M4A3E2 jumbo assault tank with its significantly increased armor protection that brought weight up by 12 tons. The same drivetrain components that powered the standard Sherman successfully transmitted power from experimental engines producing 650 horsepower without failure or need for reinforcement beyond what the original design already incorporated. German engineers calculating stress loads and safety factors tended to view such overbuilding as wasteful, excess capacity that increased production cost and used scarce materials without immediate benefit to combat performance. Every kilogram of extra steel in the transmission represented steel that wasn't available for armor plate or gun barrels. Every machining operation beyond minimum requirements consumed time that could be producing another component. Every design margin beyond calculated requirements was theoretical waste from a resource optimization perspective. American engineers understood through practical experience that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. A transmission built with 50% extra capacity didn't just handle current loads reliably, it could accommodate future engines, heavier variants, and battlefield abuse without fundamental redesign. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual tank capabilities or direct vehicle-to-vehicle comparisons. American artillery superiority that could mass fires from dozens of battalions onto any target within minutes, devastating close air support from fighter bombers that ranged freely over the battlefield hunting German armor, and overwhelming logistical capacity that kept Allied forces supplied regardless of consumption rates, combined to overwhelm German forces, regardless of tank specifications or tactical prowess demonstrated by experienced crews. But the Sherman's reliability contributed to Allied success in ways that transcended direct combat performance, enabling operational tempo that German panzer divisions simply could not match given their mechanical limitations. American tank battalions could launch attacks, sustain combat operations through continuous action, conduct pursuits of retreating enemies without pausing to consolidate, and immediately prepare for the next operation without extensive maintenance halts that consumed days of operational time. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer with each kilometer driven. The difference in operational availability determined which force could maintain offensive pressure and which had to carefully ration its
limited combat power, choosing when to commit precious operational tanks to decisive actions and when to withhold them because the risk of mechanical failure exceeded potential tactical gains. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. Evidence that came from German soldiers' own choices about which equipment they trusted for critical missions. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain large numbers of captured American vehicles to disguise their operations behind Allied lines during the offensive. German planners specifically wanted Shermans because of their reputation for reliability. Infiltration operations behind enemy lines, far from any support, meant vehicles had to function without breakdowns or access to spare parts, conditions where only the most reliable equipment offered reasonable chances of mission success. The brigade ultimately received only 2 Sherman tanks, despite extensive efforts to locate and acquire more, and only one proved serviceable enough for actual operations. That single serviceable Sherman never saw combat because massive traffic jams on narrow roads prevented the infiltration operation from achieving its objectives before Allied forces contained the German breakthrough. But the fact that German special operations planners specifically wanted American equipment for a mission where reliability was paramount spoke volumes about how comprehensively German confidence in their own vehicles had collapsed. In operations requiring vehicles to function without fail while operating independently behind enemy lines, only American equipment offered the dependability that such missions demanded. German tanks, even when fully operational at mission start, couldn't guarantee the sustained performance that behind-the-lines operations required, and German planners knew it from bitter experience. January 23, 1945, brought the final official admission of German automotive failure in a meeting of the Panzer Commission that produced a report documenting catastrophic final drive failures across all German tank types in service. The document's findings were devastating in their scope and their implications for German armored operations. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in Panzer IVs across all units. 500 of Germany's most numerous tank type sitting immobilized, awaiting repairs that might never come. 370 defective final drives in Panthers meant that hundreds of Germany's most modern medium tanks couldn't move, couldn't fight, couldn't contribute anything to operations. Roughly 100 failures in Tigers eliminated a significant portion of Germany's heavy tank force. Additionally, approximately 200 failures had been reported in Hetzer tank destroyers based on the Czech 38T chassis, vehicles that were supposed to provide mobile anti-tank capability to infantry divisions that lacked organic armor. General Wolfgang Thomele, serving as Chief of Staff to the Inspector General of Panzer Troops under Guderian, explained the operational impact in stark terms that admitted what German commanders could no longer deny. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks built to intimidate through impressive technical specifications and touted in propaganda as superior to all Allied designs, failed in the most fundamental requirement of armored vehicles, mechanical reliability sufficient to reach the battlefield and complete assigned missions without catastrophic failure that left crews stranded. Kummersdorf testing facility prepared for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin through the final kilometers of German territory, overrunning defensive positions and eliminating the buffer that had protected the capital. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical
intelligence for post-war analysis by whatever German government might emerge from defeat. Some of the captured tanks at Kummersdorf, including at least 2 Shermans that had spent years being tested and evaluated, were pressed into improvised service with ad hoc combat units desperately defending the approaches to Berlin in the war's final weeks. These vehicles fought alongside German designs in the last desperate battles, providing one final comparison under actual combat conditions rather than controlled testing. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out completely and no resupply was possible. The German tanks, including Panthers and the few remaining Tigers that had survived the retreat from multiple fronts, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability throughout their service. Tanks that had been professionally maintained by skilled mechanics in proper facilities were failing within hours of combat operations because the accumulated stress of years of inadequate maintenance, parts shortages, and material substitutions had left them on the edge of breakdown. The Shermans, operated by hastily trained German crews who barely knew how to drive them properly, kept functioning through the chaos because they'd been designed to tolerate exactly this kind of abuse and neglect. The story of War Daddy II and the dozens of other Shermans tested at Kummersdorf represents one of the great industrial disparities of World War II, a gap between nations that determined outcomes as surely as any battle or campaign. German engineers working within an industrial system that prioritized theoretical perfection over practical utility produced tanks that looked impressive on paper and could achieve remarkable performance under ideal conditions with expert crews and perfect maintenance, but failed catastrophically in sustained field operations under real combat conditions. American engineers applying decades of automotive manufacturing experience to military requirements produced tanks that lacked technical sophistication in many areas and weren't particularly impressive in specifications, but worked reliably under conditions that defeated German equipment. In armored warfare, as in most military operations throughout history, the weapon that functions when needed beats the weapon that might be theoretically superior if only it could reach the battlefield and complete its mission without breakdown. A Sherman with a 75mm gun that arrived at the objective and engaged targets effectively was infinitely more valuable than a Panther with a superior gun sitting broken down 20 kilometers behind the lines, awaiting repairs that would consume days or weeks while battles were fought and lost without its participation. Post-war analysis by American and British intelligence organizations that examined German equipment and interviewed German personnel confirmed what German testing at Kummersdorf had revealed as early as 1943. Systematic examination of destroyed German tanks abandoned across Europe found mechanical failures as common as combat damage as causes of total loss, with many vehicles showing evidence of catastrophic mechanical failure followed by hasty abandonment rather than battle damage from enemy action. Final drives broken from stress and overload, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation that occurred when cooling systems or lubrication systems failed under sustained operation. The German obsession with individual vehicle superiority and impressive specifications that looked good in propaganda and technical briefings had blinded them to the critical importance of reliability and maintainability as fundamental requirements that determined whether equipment actually contributed to combat power. They built tanks that no conscript mechanic could maintain without extensive specialized training that consumed months of Germany didn't have, powered by engines that demanded constant expert attention from skilled technicians who were increasingly dead or wounded as the war progressed, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units across multiple fronts.
Result was armored forces that looked formidable on organization charts but couldn't sustain operations in practice. Paper tigers that appeared impressive until examined closely. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany, demonstrating that the painful lessons had been internalized by survivors who'd lived through the catastrophic failures. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s during the Cold War buildup, designers consciously emphasized reliability and maintainability over pure performance specifications, reversing the priorities that had dominated German thinking during World War II. They studied American automotive engineering principles that had made the Sherman successful and deliberately applied them to military vehicle development for the first time in German armor design history. The resulting Leopard 1 tank incorporated many design philosophies that German engineers had finally learned to appreciate after years of watching their own vehicles fail while American vehicles kept running. Robust powertrain with substantial design margins beyond minimum calculated requirements. Easy maintenance requiring minimal specialized tools so that conscript mechanics could perform most repairs. Standardized components, enabling rapid field repairs without factory-level precision equipment. Growth potential, allowing future upgrades without complete redesign of fundamental systems. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies worldwide and remaining in production for decades because it worked reliably under field conditions, exactly the quality that German World War II tanks had lacked. The captured Shermans at Kummersdorf, including War Daddy II with its distinctive name still painted on the hull beneath hastily applied German crosses, represented far more than enemy equipment brought home for technical examination and evaluation. They were tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical innovation pursued without regard to manufacturing reality or operational requirements. German tank designers pursued advanced specifications and impressive performance characteristics because they believed superior technology could overcome material disadvantages and numerical inferiority that Germany faced against enemies with greater resources. They were fundamentally wrong in that assessment, as testing proved repeatedly. American tank designers built reliable vehicles because they understood through hard experience in civilian industry that logistics, maintenance capability, and sustained operational availability determine victory in modern mechanized warfare more surely than any individual performance characteristic. They were absolutely right, and their approach proved decisive in ways that reverberated far beyond tank versus tank engagements to determine the entire course of the war in Europe.
The reliability gap between Sherman and German tanks influenced not just tactical armored warfare, but fundamentally shaped broader understanding of military-industrial capacity and its decisive role in modern conflict between industrial nations. Germany entered World War II with technical advantages in many weapon systems, possessing scientific knowledge and engineering expertise that exceeded most opponents in theoretical understanding and innovative design concepts. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts who could replace losses and expand production continuously. The United States entered the war with weapons that were often less technically sophisticated in many respects when compared specification to specification, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback from units in the field. This industrial approach perfectly exemplified by Sherman.
Tank design and production methods proved far more effective than German technical sophistication applied to small-scale production. The United States produced nearly as many Sherman tanks as Germany produced tanks of all types combined, while also producing enormous quantities of every other weapon type from aircraft carriers to artillery shells, supplying allies through Lend-Lease programs that equipped entire armies, and simultaneously maintaining the highest standard of living among all combatant nations, with civilians enjoying consumer goods that hadn't been available in Germany since before the war. This economic performance, impossible for Germany to match even before strategic bombing intensified and strangled remaining production capacity, decided the war's outcome as certainly as any battle, perhaps more certainly than any single military engagement. The mathematics were simple and brutally clear when examined objectively without propaganda or wishful thinking. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt regardless of individual vehicle superiority. Reliability wasn't just a convenience factor or secondary consideration to be addressed after performance specifications were optimized. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions or sat immobilized awaiting repairs that consumed operational time while enemies maneuvered freely. German tanks consistently failed this fundamental test throughout the war, from initial campaigns through final defeat. American tanks consistently passed it across every theater, from North Africa through France to the Pacific. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943, more than 2 years before Germany's final surrender, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications in technical documents, but couldn't be relied upon to function when needed most in actual combat operations. The Sherman tank didn't win World War II through technical superiority in firepower or armor protection. It clearly didn't possess either advantage when compared against late-war German designs. It won through industrial superiority, expressed as mechanical reliability, consistent availability, and ease of maintenance that allowed sustained operations regardless of crew skill level or maintenance conditions. German engineers at Kummersdorf understood this by mid-1943, based on their exhaustive testing that had examined every component and system in minute detail. They wrote detailed reports documenting their findings with scientific precision, reports that circulated through Wehrmacht technical branches and reached senior commanders. They tested the evidence repeatedly with methodical rigor that left no room for doubt. They reached the correct conclusions about American advantages and German deficiencies, conclusions that were documented in classified reports that nobody wanted to acknowledge publicly. But understanding a problem and solving it are fundamentally different challenges, requiring different capabilities. German industry lacked the capacity to retool production around reliability principles while simultaneously fighting a losing war on multiple fronts against enemies with superior resources and reversing decades of industrial development to build the manufacturing infrastructure that America possessed wasn't possible in wartime.
American industry had built reliability into its civilian automotive sector over decades of commercial competition where unreliable vehicles meant lost sales and bankruptcy. Refining manufacturing processes through generations of experience and simply extended those mature principles to military production with remarkable success that looked effortless from outside but represented accumulated knowledge that couldn't be replicated quickly. War Daddy II, that single Sherman tank captured in Tunisia in February 1943 and tested exhaustively at Kummersdorf for months afterward, told the entire story through its mechanical reliability and consistent performance under every condition German engineers could devise. Every kilometer it drove without failure was evidence that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability, choosing impressive performance numbers for propaganda purposes rather than practical functionality for sustained operations. Every test that demonstrated American automotive excellence was proof that industrial maturity and practical manufacturing experience gained through decades of civilian production mattered more than theoretical performance calculations that looked good on paper but couldn't be maintained in field service. Every comparison between Sherman and German tank reliability proved that Americans had solved problems German engineers didn't realize they needed to solve. Problems that seemed unimportant when examining individual vehicle specifications, but became critical when multiplied across thousands of vehicles operating under combat conditions for months or years. The tank itself was unremarkable in many ways, just one of 49,324 produced by American industry, one vehicle among thousands built to identical specifications. What it represented was devastating to German confidence once the implications were understood. Proof that Germany had already lost the industrial war even as fighting continued across multiple fronts. Evidence that American productive capacity could not be matched regardless of German technical sophistication or tactical skill displayed by experienced commanders and veteran crews. The war would continue for 2 more years after War Daddy II arrived at Kummersdorf. 2 years of desperate fighting and terrible casualties, but the outcome had been determined by industrial capacity that couldn't be overcome through force of will or tactical brilliance. Germany was fighting with equipment that broke more often than it fought, while America was fighting with equipment that kept working regardless of conditions, and that difference alone was sufficient to determine which side would ultimately prevail.